Hello, my name is Santiago Avila. I'm a postdoc at the Universidad Autónoma de Madrid and the Institute of Theoretical Physics. And today I'm going to talk about the effect of the galaxy-halo connection on galaxy clustering analysis in the advent of stage 4 experiments. First, I'll start by saying why the large-scale structure is so important in current cosmology. The analysis of galaxy clustering has been one of the pillars of the ΛCDM model. In particular, the BAO has been one of the main contributors to establishing the ΛCDM model as a concordance or standard model. It constrains very well the expansion history of the universe as a standard ruler, whereas in 2010, it was helping breaking some degeneracies. In the 2020s, with many independent measurements of the BAO, mainly through the SDSS series, we can break many other degeneracies and constrain omega lambda on its own. But galaxy clustering can not only constrain the expansion history of the universe, but by measuring the anisotropies in the clustering, we can measure redshift space distortions that represent a measurement of the growth of a structure. Again, we can measure this growth of a structure in different samples and constrain modifications of gravity. We are now entering the era of stage 4 dark energy experiments. In particular, from the spectroscopic survey side, we have the dark energy spectroscopic instrument already taking data and the Euclid satellite launching probably by the end of next year. Each of these experiments will measure the redshift for around about 30 million emission-line galaxies, which will be 15 times as many as the entire SDSS series. With this enormous data in hand, we will be able to constrain much better expansion history parameters, such as the question of state of dark energy, but also growth of structure parameters. Since emission-line galaxies are a very special type of galaxies, we wondered whether their special relation to dark matter halos could have any impact on clustering or even on cosmology. That's why we started this study, in which we studied how emission-line galaxies relate to dark matter halos via the halo occupation distribution model within the framework of the extended Baryon Oscillation Spectroscopic Survey. Most of this talk is based on this paper that I did in collaboration with Violeta and other people from eBOSS. In this project, we built up on several ingredients: the outer rim embodied simulation, the halo occupation distribution model, and the emission-line galaxy data from eBOSS. The eBOSS ELG sample goes from redshift 0.6 to 1.1, and they're distributed in two areas, South Galactic Cap and North Galactic Cap, represented in blue here, that amount for 700 square degrees. We have around 200,000 emission-line galaxies within an effective volume of about 1 gigaparsec over h cubed. The outer ring simulation is a very large simulation with 3 gigaparsec over h per side and a trillion particles with a mass resolution of 2 times 10 to the 9 solar masses. We are using a snapshot close to the effective redshift of the emission-line galaxies sample. And we will be measuring the halo mass function, so how many halos we have per mass bin, and how these halos cluster as a function of mass. This will be summarized by this bias function, and these two functions will play an important role, as we will see later. So the halo distribution model tells us that the clustering of galaxies can be split into two contributions, one of pairs of galaxies within one halo, and the other one from pairs of galaxies in different halos. There were two halo terms. So this two halo term is the main component at large scales, and this will be determined mostly by the mean halo occupation. This is how many galaxies we put in average in a halo of a given mass. If we care about smaller scales, then we need to consider other properties, such as how many galaxies are centrons and how many are satellites, how we go from the average to the realization, so the probability distribution function. Then where do we put those satellite galaxies within the halo? And then what velocities we assign to them. This model can give us a connection between the galaxy clustering observations and the galaxy formation and evolution. But it could also be studied as a possible theoretical systematic for cosmology. Let's vary the details and see what happens. We start by studying the canonical HOD shape. That will be our HOD1, which is a step function for centrals and a power law for satellites. And in this case, we introduce two parameters to rescale this function up and down, because we know that not all the galaxies are emission-line galaxies. And also we introduce a mass parameter that we control left to right, where we put all these curves. These three parameters together will allow us to control the number density, bias, and fraction of satellites, as we will see. But since we know that not all galaxies are emission-line galaxies, and we know that they are a very special type, we can go and look at semiotical models of galaxy formation to know what is their occupation. We took this model from Gonzalez Perez et al. 2018 using GALFORM that gives this occupation distribution for emission-line galaxies for eBOSS. And then we fit a curve to it. We see that the satellites follow a power law, but the centrals have some decay. So we fit it with a Gaussian in our HOD2 model, and then we try to fit it better with Gaussian plus decaying power law for HOD3. As I was saying, we can put basic constraints on the HOD parameters by simply fixing the number density, the bias, and the fraction of satellites. The number of density will be an integral over the halo mass function with the halo occupation distribution functions, and the bias will also include a bias function. Now we will vary the small details and see what effects has on clustering. So we start by studying what effect has the shape of the HOD on the clustering. Here we will be fixing the number density, the bias, and the fraction of satellites for all these curves. So this is the effect it has in the projected correlation function. We see that at small scales, we see some differences between those different HOD models. But at large scales, because we have fixed the bias, they give the same clustering. We will also be looking at the quadrupole that will be very sensitive to velocities. And we see only some small deviations here. We can also study what happens when we change the fraction of satellites from 0 to 45. Remember that our fiducial model, our fiducial value is 30%, and then see what happens on the clustering. This will be the only time I'll be showing the monopole, because basically we don't see any difference because we have fixed the bias. We would see differences at the small scales, but we saw that by studying the projected correlation function, we see better the effect of what happens with the position of galaxies, and on the quadrupole, what happens with the velocity of galaxies. We see here a large variation on the projected correlation function and a mild variation on the quadrupole. This is due mostly to the finger of God effect. On the side of the projected correlation function, at small scales, we expect to see this increment of clustering as we increase the fraction of satellites, since we will have more likely more galaxies in one halo. Once we know how many galaxies in average we will put in each halo, one decision we have to make is how we go from the mean realization to a given realization, the PDF. Typically, people use a Poisson law, but in this study, we see what happens when you increase the scatter or you reduce it. And what we get is a different distribution of the number of satellites. So this, if we increase the scatter, it will be easier to have triplets, for example, of galaxies, or doublets of galaxies, right? So obviously, this will increase the clustering at the small scales in the projected correlation function, and it will also have some effect on the quadrupole. The next thing we vary is the satellite density profile. Typically, people use an Overframe White, and this will be our default model here. Then, based on some studies that suggest that emission-line galaxies tend to be in the outskirts of halos, we vary the concentrations of the NFW profiles with an extra parameter K that basically will tend to deconcentrate the distributions. As an alternative, we will also use dark matter particles from the simulation, or we could also take these particles and move them apart with this K factor again. These are the resulting profiles that we get by varying our modeling. Even if these variations may seem a bit large, when we go to study the clustering, we see that it has no effect on the quadrupole and only a mild effect on the projected correlation function. Once we've placed the satellites in our halo, we will need to choose the radial velocity profiles of the satellites around the halo. By default, we will be using the Viral theorem with the Baryon and Norman prediction. This is we add a Gaussian dispersion centered around the halo velocities with a dispersion given by the Viral theorem. Then you can introduce a velocity bias and vary this dispersion. In the cases where we use particles for the positions, we will also use their velocities. We can also include a velocity bias by rescaling the dispersion of the dark matter around the velocity of the halo. We also include one choice of info velocity in our modeling, motivated by Orsi and Angulo, where they find that emission-line galaxies tend to be infalling into the halo with a radial infall velocity of around 500 kilometers per second. Finally, varying our different choices for the modeling of the satellite radial velocity profiles, we end up with all these different profiles that we apply to our galaxy mock catalogs in the outer ring simulation. When we study the clustering, we see that this has no effect on the projected correlation function. The only difference here is due to the change in the position profiles. And we find that there are large variations in the quadrupole. In this part, we will vary the different choices in our HOD modeling that we apply to the outer ring simulation. We will measure the 2-point functions of those mock catalogs and perform a chi-square minimization with the eBOSS data. We will fit the monopole, quadrupole, and projected correlation function within these scales, but we also checked in the appendices that our results are robust against different scale cuts variations. We will show a lot of these plots in which we, on the y-axis, we vary the fraction of satellites, and on the x-axis, we vary another parameter. In this case, this is k, which tells us about the density profile of the satellite galaxies. This is the concentration parameter. So we rescale all the concentrations with this k factor. And then we fit the quadrupole, the projected correlation function, and all together with the monopole as well, which doesn't add that much, but we add it anyway. And what we find is, in this case, that WP gives most of the constraints. And then basically we recover a concentration parameter of around 25%. This gives us an evidence in favor of very under-concentrated profiles for emission-line galaxies. We also find a large fraction of satellites, around 50%. We now test varying the beta parameter that controls the scatter of the probability distribution function. And this gives us basically a constraint that data prefers a sub-Poissonian PDF. I won't have time to go through this, but we will see that this evidence goes away as soon as we vary all the details of the modeling. Now we look at the velocity bias parameter that tell us about the dispersion of the velocity profiles of the satellites around the halo. And we find evidence for it and a bias of 1.5. This is a 50% increment on the dispersion. Now, if you remember, we were also modeling an infall velocity that hasn't been included so far. If we include it, basically what we find is a shift in the alpha parameter, the velocity bias. So in this case, the evidence for the velocity bias goes away as we recover the fiducial value of 1. So we recover the standard dispersion. But of course, this infall velocity is also adding something equivalent from the clustering point of view to that dispersion. In the literature, most of the people, when fitting HODs, they only fit the shape of the occupation function. So we'll look at that now. In this case, we see what happens when we go from HOD 3, our default value here, to HOD 1 or HOD 2. We see that in the case of HOD 1, everything gets compensated by lowering the fraction of satellites, whereas in HOD 2, everything gets compensated by increasing the fraction of satellites. But all the dynamical parameters of the PDF, the profiles concentration, or the velocity bias remain exactly the same. So basically, everything can be absorbed by changing the fraction of satellites. This is, we find a subdominant effect on the shape of the HOD. In the paper, we also ran other fits varying different model choices, such as adding the particles, and also we tested for the degeneracies between different parameters. If you want to look at the details, you can go to the paper or either go to the appendices of these slides. But here I will summarize what are the results of all those fits. The general conclusions we can draw from all of that is, the main one is that we find in all cases a clear consistency in preferences for under-concentrated profiles. This can be from K of 0.15 to 0.4. This K factor is also key in order to obtain a good fit to the data. We have found the mean HOD shape subdominant to the rest of effects. We find some mild evidence for high velocity bias or infold velocity. We find the slight preferences in the chi-square for particle profiles. The best fit fraction of satellites is very susceptible to the rest of choices in the modeling. As for the PDF, we find it very sensible as well for the rest of choices, and we don't find a clear preference for either Poisson, sub-Poissonian, or super-Poissonian PDFs. So at this stage, you might be wondering whether all these choices of the one halo term, how we distribute the galaxies within the halo, are really relevant for cosmology. So what we did within the eBOSS collaboration is to run all the eBOSS pipeline analysis used for the final ELG data and run it through all the mocks that we generated, varying the mean halo occupation distribution, including the fraction of satellites, the PDF variations, the position profiles with different concentrations or particles versus NFW, different velocity profiles with different velocity biases, particles versus viral theorem versus infold velocity. And we ran all the cosmology pipeline recovering rest space distortions, radial VAO, and angular VAO. As you see, you find some scatter even if the underlying dark matter simulation is the same one. Given this dispersion, we decided to report these gray bands as our systematic error on the theory. And this was completely negligible compared to the statistical error bars of eBOSS. However, as we go to next generation of surveys, increasing the statistical precision, but also wanting to go to smaller scales, we will need to revisit this very carefully and see whether we need to improve the modeling. Finally, you have a model and you want to test them against all these mock catalogs. You can find the galaxy catalogs in this link and let me know if you have any question about them. So you might be wondering how it can be that the cosmological fits are affected by the one halo term choices. First, remember that the quadrupole can be affected up to 50 megaparsecs in the case where we vary the different choices for the velocity profiles. But also, if we go to Fourier space, things are more mixed up. This is the power spectrum for the HOD variations and the PDF variations. We don't see much of a difference for the PDF case, but already varying fraction of satellites have a large impact. This is the finger of God effect, of course. But then once you go to velocity profiles variations, you see that this range of variations is quite large. So this needs to be understood in very detail in order to model it properly. Again, in this case, the position profile seems to have a negligible effect. Finally, I will comment on the future prospects and on the conclusions. So we are now moving forward with a new suite of simulations, mainly the unit simulations that using the trick of the fix and pair, cover an effective volume of around 7 times larger than Euclid or DESI. And it's ideal to test clustering models. Within the group in Madrid, we are working with these simulations, and a recent paper by Alexander Kneve presented the emission-line galaxies added to this simulation with the SAGE semiotical model and the get emins codes. The catalogs are already available. And now we are studying what happens with the H-alpha galaxies that will be seen by Euclid, studying the galaxy halo connection. And we are also generating some mocks for the DESI survey. To sum up, we have dissected the assumptions that go into the HOD model, in particular with a focus on emission-line galaxies. We have studied how the detailed choices of mean halo occupation distribution, satellite probability distribution function, satellite position profiles, and velocity profiles can affect galaxy clustering, motivating the different choices with previous observational and theoretical studies. Remarkably, we found that details on the PDF or the profiles can affect more the clustering than the shape of the mean halo occupation distribution. Using eBOSS ELG data, we found a strong and robust evidence of under-concentrated ELG profiles, and including this is key in order to fit the clustering of the data. We found the galaxy halo connection to have an impact of galaxy clustering that could potentially also have consequences on cosmological inferences, but we showed that this is subdominant for eBOSS. However, future surveys that are expected to have smaller error bars will need to revisit this. In those lines, this will be particularly relevant for Euclid and DESI that will rely on emission-line galaxies. The catalogs used for this study are made publicly available in this link. Let me know if you have any questions, and thanks a lot for listening.